Welcome to Velocity Divergence, world's first flight simulator that fully solves the Navier-Stokes fluid equation everywhere using a direct numerical method. Your airplane is simulated solely based on the shape and the angle of its wings, without making any assumption of any specific flight model. Therefore, it behaves exactly like an airplane would in real world, even in situations such as tailside and tumble, often not represented in other flight model based sims. In this video, you will learn some of the basics of flying. There are only two controls needed in this game: throttle and elevator angle. Left and right movement of your mouse or finger sets the throttle. Up and down controls the elevator angle. An airplane is designed to be nose heavy, so without any input, it will gradually drop nose first, losing altitude in exchange for airspeed, which refers to the speed of airflow over the wings. After there is airflow over the elevator, changing elevator angle causes the airplane to pitch up or down. If you pitch down, you trade away altitude for more airspeed. If you pitch up, you trade away the accumulated airspeed to reduce your rate of falling or vertical speed. The trick for a good landing is to know when to start pitching up or to use accumulated airspeed to arrest the descent or to flare. If you flare too early, you may use up your speed energy reserve before it is needed. Subsequently, gravity causes vertical speed to still increase, resulting in a hard touchdown and damage because you don't have enough airspeed anymore that is needed to pitch up or to arrest the descent. If you flare too late, there may not be enough time to complete the transfer of energy out of airspeed, also causing a hard touchdown and damage. The very best landing is when you transfer all energy out of airspeed just at the moment of touchdown. Your airspeed will be near zero and your vertical speed will be the lowest it can possibly be. Until this point, I did not use engine throttle at all. With throttle, you can gain both airspeed and reduce vertical speed. With just a bit of throttle, you can reduce the touchdown vertical speed to almost zero to achieve the softest landing. To get a feel of the airplane, a good practice is to try to maintain a constant altitude using the least amount of engine power. As engine power is reduced, airspeed reduces and you need higher pitch angle relative to airflow or angle of attack to generate more lift to cancel gravity in order to maintain altitude. But there is a maximum angle after which higher angle of attack will reduce lift instead of increasing it. When you exceed this maximum, lift produced by the wing drops. Since your elevator at a lower angle of attack is still producing lift at the tail, this causes the airplane nose to drop. This nose drop is called stall. As the nose drops, you lose altitude and gain airspeed, which causes the wing angle of attack to drop below the maximum angle. Wing starts to produce normal lift again and everything repeats. Note that this loop is self-sustaining and I am not touching the mouse or any other input here. This pitch down, faster, pitch up, slower, pitch down oscillation is observed to some degree in anything that flies, from paper airplanes to jumbo jets. One thing other flight sims don't get correctly is tail slide, or when the airspeed becomes negative. Because the airspeed over the elevator is negative, it works in the opposite way. To pitch down and fall canopy up, you need to pull the stick or move the dot up, which normally would pitch up the aeroplane. On the other hand, to keep pitching up and fall inverted, you need to push the stick or move the dot down, which is the direction that normally causes the airplane to pitch down. To make the game fun, power to weight ratio of some airplane is quite high. Like one can do donut in high-powered race car if one floors the gas pedal while turning to one side. You will find the airplane sometimes enters seemingly uncontrollable self-sustaining tumble. Wind created by the propeller, also known as slipstream, takes a small but finite amount of time before it hits the wing of the airplane. If the airplane is already rotating faster than a certain rate, the angle of the wing would have changed sufficiently during this delay, causing the slipstream to generate a torque that reinforces the rotation, making it rotates even faster. This is why such tumble is self-sustaining. Because the average airflow over the elevator during rapid rotation is quite small, the elevator effectiveness is low, making it appear the airplane is uncontrollable. To stop the tumble, simply reduce the power to 0%. The natural stability of the airplane should cause the rotation to slow down sufficiently and air flows over the elevator again. Then apply the full opposite elevator to stop the rotation and fly away.